possible ways and create a bunch of successor graphs. And then you do the same to all these successor graphs again and again and again. And for some reason, sometimes you will end up in the same graph from two different ways or in two different ways. And so you need something to identify similar graphs, which is something that we do. We have learned that from Arendt, how to do it on the groove system. And so we compute this reachability graph. And for case A, this is already enough that you need to do. Then you apply the metrics to all the possible clusterings that you can have exhaustively, and then choose the best one that you're done. For case B, it's already no longer possible on my machine to compute the whole state space. So you need some more thinking about it or reduce it. So we actually added an A star-like approach, which is actually saying from all those successors, just apply the matrix to them, and then only expand the V1, which has the best metric value. So we apply a CRA, the original computed metric function, to it, and then just go for the best one. That was actually the first thing that we did, and that was pretty nice also. And it's to some extent low time. However, once you are down there and it doesn't improve anymore, it starts backtracking. So you actually keep all those previous graphs. So actually you have a list of graphs we did not yet expand, and this is sorted by the metric value they have. And when you are done with the best one, you add the successors of those, and if those successors are poor, then, or there are no more successors, then you just go for some of the graphs you have considered earlier. That's the full point. So that's a depth first search algorithm. That one went fine for B, no longer for C or D, because it already was still, well, you keep copies of all those graphs. And when days are up to some million, it starts to, well, fill your memory up. And so that's the thing you shouldn't have done. So what you actually said is, as soon as we find a successor of the current situation that is improving the situation, don't look at the others. So we actually say, the first one that is better than the current one, I go for that one. And only then for this one, and only for that one, and only for that one. And now it's actually hill climbing at the end. Still, we do the backtracking thing once we are running to top of the hill and cannot improve anymore. Then we go back and say, okay, this one has now 2. Let's have another one of those, and another one of those, and these kinds of stuff to look in other places around. So it does a search in this search space. And then we actually said, okay, this one performs kind of, well, reasonably fast, because we just go right to the hill and that's it. And then you do some backtracking, and usually it doesn't improve anymore. So it has been one case where it actually, in case B or C, when you run it for half an hour, then oops, yes, I now found a better one. So actually searching down here pretty much, let me go for another one. If this is our search space, it goes down here, and then it actually explores this space down here. And there might have been a point where it should have gone here. And that didn't he actually find reasonably. So what we then did is a variation of that, where we said, okay, if there is a list, if we have a graph and we expand it, we actually go through all its successors, but we only keep as future candidates those that are an improvement in this set of things. So we go for the first one and say, oh yes, this one seems to be a good one. Then go for the second one and say, oh, this one is even better than the first one, so don't look at this one anymore. And then we say, okay, oh, actually no. We say this one is, we keep that. This one is poorer than B2 we already have, though we said, no, this one I'm not going to look at, and so on and so on. So we actually throw some of those successors out for no good reason, just to save space. And this mixed version somehow managed to find a good solution, a better solution than the other versions in one case. And so we didn't think, okay, we cannot let it out. At the very end of this, well, the genetic algorithms are outperforming us. So we are still in one branch, in one edge of our search space. We look pretty good. We do some backtracking, but if the branching should have been done pretty early in the search, we are not going to find it. So perhaps in the phases of simulate annealing, our temperatures is too cold, we are not going back far enough to find other solutions that are in other parts of the state. What's good about the solution is it well, improves the situation pretty fast. This is because we start with this unclustered graph and then we just improve all the time. Any clustering we do actually usually improves the thing. And I think it's in the nature of this problem or of the examples that the hill climbing thing works pretty well. So all of our variants go towards this first hill pretty fast. And actually we can go on, we have all the graph we have visited in our main memory. So at any point in time we can actually say, okay, I have now visited some 100, some 150, some 200 graphs or situations. And this is the CRE index I have already achieved, the best of them. And then you can say, okay, 100 steps later, how good am I now and how am I now? And you see this curve. It goes up from pretty bad to pretty good very soon, and then it doesn't improve anymore. So you actually can then say, okay, it's running now for 10 minutes, it's no longer really improving, I can stop it. That is something that is, at all the time you get the feeling about how good is the solution I already have, which is something I think is more complicated for the genetic algorithms. They have this, well, GPU or these some 500s, and I'm not sure whether we have actually a feeling about, could I stop it now, or is it going to improve further, or yeah, you say you can? Okay, you say, I like this picture actually, you can see how good you are already and can stop it anytime. So after all, we come up with reasonably good CRA values, which are computed by, well, variant of those algorithms. Actually, you need to run them all three, and then look which one performs best, and then you take that one. Actually, so if you actually apply all three, those time numbers are cheating. Actually, we were looking at these curves, how is this improving, and if it's not, then we run it for an hour, and if it's no longer improving, we take the last point, it was improving, and put this on the performance numbers. So that's not fair. So this is the time that he optimally uses it. We did not do random experiments because there's no randomness in here. It is all deterministic. If you run it multiple times, you'll come with exactly the same tree or search space exploration that it's done before. So, well, yes, it may vary in performance time a little bit,